second speaker will be Frederi Viens, who will talk about application of Stein's lemma in Malliavin calculus to the densities and fluctuation exponents of stochastic heat equations.
Thanks very much for the introduction. And I'd like to thank Gislav and Michael for the invitation. It's very kind. And it's very impressive to be here with such a distinguished audience. Some things, yes, you're recording. I can speak louder, but I know you're recording. How's that? Better. Well. All right. So it's going to be a Blackboard talk, unfortunately for you guys. And the subject of the talk, I was very impressed and inspired by Professor Marta Sanz-Soleil's talk this morning, in which she really made an effort to explain to folks like those of us who don't completely understand the entire theory a little bit what it's about. So I'm going to try to imitate her a little bit on the subject of Malliavin calculus. And my purpose is to try to advertise some techniques that my colleague Yvan Ourdin and his colleague, and I guess hopefully also in the future my colleague Giovanni Piccati and I are trying to put together to utilize Malliavin calculus in an efficient way. That's kind of going to be the first part of my talk. The second part will be connections to Stein's lemma and a tool which we use, which is a density formula that Ourdin and I discovered, which we will then apply to general density estimates and concentration inequalities for general random variables, which can be expressed in a framework where everything is in terms of an underlying Gaussian process. And as applications of these tools, which is the main purpose of my talk today, I'm going to talk about things that are related to the topic of the workshop, stochastic PDEs. I'll talk first about a fluctuation exponent, which I've derived for a linear multiplicative stochastic heat equation, and then perhaps more impressively, a paper which appeared, I forget where, but I think I have it written somewhere, by David Nouellart and Luis Caradagnos on how to estimate the density of the solution of a linear, I can't remember if it's quasi-linear or semi-linear, I always get them confused, stochastic heat equation with additive noise. So the framework here in part one is on Malliavin calculus, and what you want to start with is a Brownian motion. Let's say, to make things simple, we'll take it on 0, 1. And the notation that folks like to use, if you have a function which is in L2 of 0, 1, you're going to integrate this deterministic function with respect to your Brownian motion, and that's going to give you a centered Gaussian random variable whose variance is equal to the squared norm of f. And the inner product between two functions in L2 of 0, 1. I'd like to know if you guys can actually see the print. I don't know if it's too small for the people in the back. It's OK. The inner product in this space L2 of 0, 1 is going to be also for those two functions, the inner product in the L2 space of the Gaussian random variables, which are the integrals of those two functions. And then the Malliavin derivative operator is something, I'm not going to define it completely formally, but I can tell you that there's one really easy way of finding at least one example of a Malliavin derivative. When you take a random variable which is Gaussian, under this, we're inside a space where everything that is linearly related to W is going to be Gaussian. So this is a Gaussian random variable, and its image under the Malliavin derivative is the function. So it's kind of taking the function out of the integral with respect to W. And you have also the chain rule, which in this case is very simple to write. If you have a function capital phi, which is continuously differentiable with maybe a bounded derivative, and you apply it to this Gaussian random variable, then if you take the Malliavin derivative so by the way, this means that generally speaking, so you can write, maybe just let me be specific here. There's a time parameter as an index of the operator d. As you see, this function f depends on time. It depends on time. So this notation here, which I have over here, is equivalent to this notation over here. The derivative Malliavin derivative at time r of w of f equals f of r. And so here, if I do the same thing right here, I'm going to get a chain rule, capital phi prime of w of f times little f of r. So this is the chain rule in the simplest possible situation. And then the chain rule more generally, if you have, if you're looking for the Malliavin derivative of a function of several random variables, in fact, let me write it even more generally. If these are L2 random variables which perhaps have Malliavin derivatives, and you stick them inside a differentiable, continuously differentiable function, then you're going to get that this is the sum for I equals 1 to n of the partial derivative of your function. It's just the chain rule applied to these vectors multiplied by the derivative of the ith random variable. So that's the chain rule for Malliavin derivatives. Yes. This function f is deterministic. And so this is just a way of saying that you can take, for instance, a capital X which is of this form, but you can take it more complicated. You can take a capital X which is actually of this form, but everything is consistent. You just construct everything that you want for this Malliavin derivative just using this simple chain rule. So if you want to simplify the last statement that I've made down here, just think of each of these x's. Each of these x's, think of them as w's of f's and g's.
No, I simply got used the Malliavin derivative with the random function rather, and here in your chain rule it is random.
I'm sorry, could you repeat that?
In your chain rule, the result of the chain rule is a random function, not a deterministic one.
The Malliavin derivative of a random variable which is not Gaussian is typically going to be random. Yes, that's correct. The space which is usually called U12, it's a Sobolev space in the Malliavin sense, is going to be all the random variables that are square integrable with respect to the omega where the capital W lives, such that the integral of the Malliavin derivative is finite in the space L2 of omega cross 0, 1. So this is the definition of this space D12. And then there's also the chaoses, which we heard a little bit about in the context of Wieck products just a little while ago. And here I'd like to describe them a little differently. The nth chaos is the space of all the following types of random variables. Random variables which are written as multiple integrals of a symmetric function with respect to the original Brownian motion. This is a multiple Ito integral. The function f is deterministic, so that means that after you do one integration, you'll have an adapted process which you can then integrate again, etc. And the n factorial is simply there because here we're integrating over a simplex. We're integrating over a simplex because it's easier when you're just using Ito integrals. At least the statement is clear, or so I hope. And then this expression here, I will give it a name. I'll call it In of f. So it's the multiple integral of the symmetric function f. F is in L2 of 0, 1 to the power n. And it's symmetric. That makes things a little easier. And there's a very important property, which is that L2 of omega is equal to the direct sum, in the L2 sense, of all the chaoses. That means that if you take x in L2 of omega, you can write it as a sum of things of this form. So there exists a sequence of functions fn which are symmetric in L2 of 0, 1 to the power n, such that x is equal to the summation well, we can write it as expectation of x plus integral plus summation n equals 1 to infinity of I n f n. So it's an abstract, I mean, it's very concrete in some sense. It's also kind of abstract, but it shows that there's a representation for every square integrable random variable, which is measurable with respect to the sigma algebra generated by capital W. And then you can also, so it turns out, here's something that may not be useful for this talk, but it's certainly not unuseful in general. There's another way of determining whether a function is in this space up here. You write the function this, you write the random variable capital X this way, and then if its coefficients are summable in this sense, then that means that the random variable is in D1 too. So I won't go into the details of why that works, but it's a convenient representation of D1 too. And here is the one thing that I think a lot of people think is kind of mysterious when they look at a bit of Malliavin calculus, but it's, in this context, it's completely trivial. There's this operator which is called L, which is the generator of the Ornstein-Uhlenbeck semigroup in the Wiener space. Yes, sir. How's that? Più alto. Ah, grazie. Così. Ah, troppo. Ah. Così. So L, it's the generator of the Ornstein-Uhlenbeck semigroup, and I'm not really interested in L. I'm interested in the opposite of its inverse. And it's very easy to write. If you take a random variable x of this form, then here is L. So it's nothing mysterious. This is the expression for L. And so typically you want to, this is the expression for negative L inverse. You want to assume, here we are assuming that expectation of x equals 0, so that there is no term here at the beginning of the sum of the chaos expansion. So that's for L. And then, this doesn't move, does it? Oh yeah, it does move. Wow. Incredible. See, in the United States, we're a backwards country, and we don't, I mean, at least in the Midwest where I live, there's nothing like this.
It's not true. It's not true.
So which part of the Midwest do you have? Where? In Kansas, perhaps. Here is the main object of study that I want to investigate. You're going to take a random variable x in L2. Therefore, I can write it using its chaos expansion. And then we're going to define a random variable g, which is equal to the following inner product. You're going to take dx. You're going to take d of negative L inverse of x. Take the inner product of those two things. And this is a new random variable. So for instance, if x is Gaussian, then dx is a non-random function. In fact, you know, there's a sort of characterization. It's not true that every Gaussian random variable in Wiener space has a non-random Malliavin derivative, but it's certainly a good indication that that's the case, that it's Gaussian. So if x is Gaussian, then you can, so let me put it this way. If you have a Gaussian random variable, you can always construct a general Gaussian space or even a single Brownian motion such that the derivative of that random variable with respect to this Brownian motion is non-random. So let's assume that's what we have. So if you take x, which is Gaussian, this is a non-random function, just like this one over here, f. And then if x is Gaussian, you'll see that, what is the Gaussian case? If you look at the expression, where's that piece of bamboo that I saw earlier? Oh, here. If x is Gaussian, and let's assume, of course, that it's centered. I'm going to assume that throughout the entire talk. This is 0. If it's Gaussian, the assumption that I just said is that this sum is reduced to only its first term. So that means that if x is Gaussian, negative L inverse of x is actually equal to x, is equal to x, yes? And as you can see from this expression. And therefore, dx is going to be equal to the f that it comes from, and this is also going to be equal to f. And so this whole expression will be the inner product. It'll be the square norm of f. So when I have a Gaussian random variable, I expect the random variable g that is constructed with that Gaussian to be a non-random value. But if x is not Gaussian, you're going to expect g to be random. And in fact, you can prove that x is going to be Gaussian if and only if g is almost surely a constant. And so certainly with the tools that I have up here, you can compute g. But there's also this thing called, it's a consequence of what we call the Miller formula. And here it looks kind of funny, but it's not all that complicated. Let me write it down, and we'll see how you guys react. You have, what you're going to do is you're going to take two Brownian motions, the original w and another one which I will call w prime, and you're going to construct a correlation of these two Brownian motions. I'm going to explain all this crazy notation. It may not be worth my time, but I'll do it anyway. You know, Americans are always trying to be efficient, right? So you take a Brownian motion w, another one w prime, and you take wu equals w times e to the negative u plus w times the square root of 1 minus e to the negative 2u. So this is this wu for each value u, which is affixed to a positive number. This wu is a Brownian motion, and it's correlated to the other two, and these two are independent of each other. And so my notation here is that every random variable can be expressed somehow as a functional of the path w. So that's what this expression is. It's the functional as a function of w, and here it's the same expression. And so when you take this inner product, which makes complete sense if you understand x as a functional, and if you understand the operator d as an operation on the functional itself, this makes sense. And then you have an expression here which depends on both w and w prime. You take an expectation with respect to the w prime, you kill the w prime, but you don't kill the w. So this whole thing's random. It's like a conditional expectation here with respect to the w prime.
So you're independent?
Pardon me?
Independent?
Independent, yes. So anyway, it doesn't matter so much. It's just that I'm just presenting a bunch of tools and maybe not justifying them so well. But the point is that this tool is useful. And so why is G relevant? So here is how you can use some of these tools. So the first thing that I want to talk about is result of Yvan Ourdin and Giovanni Peccati. And Giovanni Peccati told me that he can't stand it when people misspell his last name. And so every time I write it down, I'm not sure, but yeah. Article which appeared at the beginning of last year says the following thing. It turns out it's deceivingly simple. This is a very, very simple remark, if you will, that they make at the beginning of their article. If you take a random variable x, and I should say, assume, as we do, that x is centered and is an element of L2 of omega. And then if you assume that, then you get the following expression. I'm sorry, not an element of L2 of omega. It's an element of D12. So it's more restrictive. If you have a random variable which is Malliavin differentiable, then the g is going to be properly defined. And if you want to compute this expectation here on the left, it's the same as computing g times f prime of x. And this is going to work for any test function that's not too nasty. Test function f. And in a certain way, this goes back to Stein, but in fact, the connection here is the connection to Malliavin calculus, which is in the expression for g that we have up here. That's the connection. So if you compare this to Stein's lemma, and I have to admit that I'm a novice in this area, but Stein's lemma in a very simple form, you're going to fix a number z, and you're going to let capital Z be a random variable which is n01. And then there exists a solution f which is piecewise in C1 and continuous with the infinity norm of f less than or equal to, I think it's 2 pi or square root of 2 pi, and the infinity norm of f prime which is less than or equal to 1. So there exists such an f that solves the following ordinary differential equation. You take the indicator function of the interval from negative infinity to z. You subtract the CDF of the standard normal, and that's supposed to be equal to f prime of x minus x times f of x. If you take this lemma of Stein and you replace capital X replace little x by capital X and take expectations, then you're going to get a slightly different statement. And what you'll get is that here, the expectation with little x replaced by capital X in this last term right here, you can use the formula that I have right over here. Okay. So let's do that. So I mean, I'm saying it's extremely simple, but you had to think about it. And this is what Nilda and Picati did. So you end up with, for x as in over there, you end up with probability that, so the tail of x minus the tail of z, so minus the normal tail, is equal to the expectation of gx minus 1 multiplied by f prime of x. And you know, the f prime here is the solution of the Stein equation. Therefore, it depends on little z. But this statement here holds no matter what little z is. So in a sense, you have uniformity. If you wanted to compare the distribution of x with the normal distribution, you could stick absolute values around here. Yeah. You can throw them inside. That means that you're looking at how close g is going to be to the value 1. G is random, but it might be close to 1 somehow. You can get rid of this term completely if it so suits you. And in many cases, this is even the right thing to do. It's not unsharp in many cases. And so you see that depending on how close g is to 1, so if we write this, we're going to get this statement. So it helps you understand how close your distribution of your x is to the standard normal distribution. So here's a theorem that uses this sort of idea. You have x in D12. I need another piece of chalk. Centered. And you assume there are some regularity and integrability conditions on the density of x. So we assume that x has a density with respect to the Legge measure. The law of x has a density with respect to a Legge measure. OK, I mean, there's ways of proving that sort of thing using Malliavin calculus in a different way than what I'm doing here, so I won't go into those details. But if x has a density, it has some regularity and integrability conditions, then you get the following statement. If g of x is greater than or equal to the constant 1 almost surely, then the tail of x is bounded below by the Gaussian tail, multiplied by some sort of a universal constant. So you need some regularity. There are some coefficients that go into these conditions which are going to determine this constant here, but you have this lower bound. So it's a way of computing lower bounds for tails of random variables. If your g, which is random, is non-random and non-degenerate enough that this holds, then you have this very simple lower bound.
Excuse me, in the second line, we have on the left-hand side we have z, and on the right-hand side we don't have z.
My bad. Oh, no, that's right. No, that's right. Z is a Z. I'm sorry, I'm American. I apologize. Z is a parameter.
Yes.
Z is a parameter, and this F. And I was trying to make it look easy, and you're right. I should have thought better of it. This F depends on Z.
Okay.
Yeah.
On the random variable.
It's not a random variable. It's a fixed coefficient. It's a fixed number.
But you also get a random variable.
That's a capital Z. I'm doing my best.
Okay.
Yeah. Let's see. So here's another. So this is an article that I wrote by myself. I think the last time I wrote an article by myself was maybe 10 years ago. So I was pretty proud of myself. This appeared actually in SPA, so it's not a bad journal. And then maybe one of the referees is in this room. I don't know. And then here's another theorem. This is a density formula. And this is by Nourdin and myself, and this is a Electronic Journal Probability 2009. And so here's what you do. If you need more information than what you can gather from this sort of very simple statement, you can try to have a better control on the random variable gx. So what if not only do you have a lower bound on g, but you also have some sort of upper bound on g using another constant? I mean, that could happen, and I'll show you an example where it does happen. That could happen. Then with an upper bound on g, can you make more specific statements? Well, before you do that, here's what you can do in general. So here is a function which depends on, so this is a capital X. This is a little z. You define the conditional expectation of g given x. Yeah. So this is a non-random function because I've specified the value of x here. And it turns out that, I guess you can just, I mean, there's several ways of going about it, but you can say that if rho x equals the density of x, and here, of course, you're assuming that x is centered an element of D12. If it has a density everywhere, let's say, then here is what the density is equal to. You have a formula for the density. So we have an explicit formula for the density. So I'm saying that if you're able to understand something about this conditional expectation, okay, a conditional expectation could be as hard as anything, but if it's not too bad, then you have an expression for the density of your random variable. So it's worth trying to express this sort of conditional expectation because it gives you a lot of information right here. And it turns out that this is actually a special case of a much more general result, which was, I believe, written down in Malliavin's book, Stochastic Analysis, and in which also Hélène Hérault from the University of Picardy collaborated on. And perhaps she was even at the origin of the whole thing. I'm not really sure what the history of it is. But those two fellows, Paul Malliavin and Hélène Hérault, Hélène is a woman, I shouldn't call her a fellow, have a much more general framework where this formula also comes in. And we noted this in an article which appeared last year in JFA. This is an article that I wrote with Malliavin and Hélène Hérault. But you know what? You guys should have told me. You were watching me before, and then you let me slide here, right? I was supposed to do this. Yeah. So I heard that Professor Zabchik, and I apologize for missing his talk, actually did a better job of the board work than I just have done. So so here's an interesting here's an interesting application. Assume there exist two constants, c and c prime positive, I'll say something about that in a minute, such that almost surely g is sandwiched between these two constants. Assume that. And that can occur. I'll show you an example in a minute. Then what you're going to get is Gaussian lower bound and upper bound on the density. In fact, you don't even need to assume that the density exists, because the lower bound assumption on G guarantees the existence of the density. And these are fairly strong conditions, I admit. The reason I know they're so strong is because the conclusion is so strong. You end up with these lower and upper bounds. If you want an upper bound on rho, you're going to replace this G here by the lower bound C and this G by the upper bound C prime. There's your upper bound. And for the lower bound, it's the other way around. So if you're in a situation where you believe that you have lower and upper bounds of Gaussian type on your density, then my advice is, well, see if you can get a handle on this function and try to prove this condition. Because I believe in some sense, and we haven't proved it, but I think that those things are equivalent. Maybe it's trivial, in fact, I'm not sure. So here is the first application I want to talk about. So there's two applications to SPDEs. Here is the one that I included in my article that appeared in SPA. So you have the stochastic heat equation with multiplicative noise. And, well, I'm sure that you could do better, but here's what I did. Here's a stochastic heat equation, which you can write in its strong form if it occurs that the solution, strong solution, exists like this. So U is the solution of the equation. Here's a Gaussian noise. This Gaussian noise, capital W, is a Brownian motion in the time parameter. You assume that the space parameter is in maybe some sort of Euclidean space, or maybe a torus or something like that. It doesn't really matter what you get. What's more important is how you define the covariance. This is, W is Brownian in S and functional in X. I just mean that it's a function in the X parameter. It's not a distribution. It's nothing as fancy as that. So you know that for the stochastic heat equation with space-time white noise, you're going to get a solution. But I can't go that far. I have to assume that W is functional in the space parameter. So when I assume that, then I'm going to assume that the expectation so let's write it this way. You assume that W is centered. It's a Brownian motion in space, and it has a tensor product form for its covariance function. You're going to also assume that the random variable, the covariance function Q. So W has a spatial covariance function. I call it Q. And so I make a very strong assumption on it just to see how far I can get with these methods that I've written over here. And what I'll assume is that Q is bounded above and below by positive constants. I mean, that can occur. And so one example of that is if you have this equation on a torus, then it's more than likely that if correlations are all non-negative, then they will also be strictly positive. That's not a bad assumption. So if your covariance function is continuous, that's going to be true. So here's the assumption that I make. And then I won't go through any of the details. But what you'll do is, the first thing that you'll do is you'll write U as a Feynman-Katz formula. I forgot to mention that this is integration, if you want, in the Svrtanovich sense. You make that assumption. And the expression for the solution using the Feynman-Katz formula, is like this. I'm trying to make the problem as simple as possible. There's a initial condition which is 1 all the time. There's no initial condition here. As you can see, it's just 1. And here, what I'm doing is this EB is not the same expectation as the one that I've been using. This is a completely separate probability space. It's the one where little b is a standard Brownian motion, or maybe a Brownian motion with speed 2 here, or square root of 2, which represents the Laplacian right here. So it's a standard Feynman-Katz formula. There's no problem there. And there's no correction term because I'm using the Stratanovich sense. And so it's a very simple manipulation. What you do is you take the logarithm of u, and then you ask yourself, this is a conjecture that physicists had regarding this equation. And I think the person who knows best about this, I won't get too deep into it, is Sami Tyndall. And so the conjecture is that in discrete space, here you can be discrete or continuous, it doesn't make any difference. So the conjecture is that in discrete space, it makes sense to talk about space-time white noise. Here, it is a function of space, space-time white noise in discrete space. Discrete space ZD. Yeah. Conjecture is that the variance of the logarithm of u grows like a power of t as t goes to infinity. And this power, which we'll call alpha, is called the fluctuation exponent. It tells you how much fluctuation there is in your system. The conjecture is that alpha is strictly larger than 0 and strictly less than a half. And here, I get so if you let, maybe I'll write it in this corner here, you're going to get the question is whether variance of logarithm of utx is of the same order as t to the alpha, with alpha between 0 and 1/2. Proving that alpha is less than or equal to 1/2 is trivial. Proving that alpha is greater than or equal to 0 is trivial. The physicist's conjecture is that these are strict inequalities. And in this situation, we prove that alpha equals 1/2. So it's not a counterexample to the physicist's conjecture because they were talking about space-time white noise. But here we have something which is not at all space-time white noise. It's time white noise, but in space it has a positive correlation everywhere in space. So even if you're in infinite space, it's maybe not a physical model in infinite space. You have an infinite correlation into the distant reaches of the universe here. So we show here that you have to be a little bit careful when you talk about this sort of model because depending on how strong your correlations are in space, you can end up with something which is not at all what people's intuitions are. And we prove this simply by looking at the random variable capital X equals log of u and applying this theory here. I won't even write it down because all we do is we compute log of u, then we compute the g corresponding to log of u. T is fixed, x is fixed. We show that x doesn't make any difference. We show that with t, we end up with a statement just like this, except that you have square root of t on both sides. So that's what we prove. You divide by square root of t in order to get the scaling that you want, and then it's an immediate application of this last remark right here. So it's really quite simple. And then the other thing that I did was, have I been saying we instead of I? This is a paper I wrote by myself. I'm not the Queen of England. Who am I kidding? OK. So I also proved that if you take a W which is, in some sense, a mixture of Gaussians, which may have very heavy tails, then the same phenomenon occurs. And of course, much more is true in the Gaussian case. You get these density estimates. But in the more general case, you get that this variance does behave like this with alpha equals 1/2. So that's the first application I wanted to talk about. And then the next one. So that was part 3. I think I missed part 2. This is part 3. Did I disconnect the? Can you guys still hear me? Yeah. And then part 4.
You could have also one-dimensional inner process.
Pardon me?
You could have also one-dimensional, but degenerate noise. As if,
That's correct. Yeah. So it's a very extreme situation because the case of degenerate noise is very different from the space-time white noise in discrete space. And so I believe that's why I still believe in the physicist's conjecture.
Sorry, you said that you settled down this conjecture.
Pardon me?
You said that you proved.
No, I found an example where the conjecture does not hold. And presumably this is because the case of positive correlations over infinite distances is extremely different from the space white noise case. I mean, it's obvious, actually. That's the reason. But again, I apologize for repeating myself. I think that this is not such a crazy example as one might think, because if you're on a torus of any size, and you're assuming that you have non-negative correlations, the chance of you having actual zero correlation somewhere is going to be, in terms of modeling, very unlikely. And so this result will apply in that case. So it depends on what kind of physical world you're living in, that's all. So the last example, which is perhaps more interesting than this one, is by David Newellart and Louise Kerr. And my apologies, where did this appear? Is Kerr here?
Last year.
Where?
Where? In SPA.
Ah, excellent journal. I agree. So let me first start with the dimension 1 case. We have dimension 1, and we have, again, Luis, please remind me, is it quasi-linear, or what is it, quasi-linear? Is that the name of it? He doesn't remember
Yes,
either.
quasi-linear.
Oh, quasi, okay. So we consider the quasi-linear stochastic heat equation with additive noise. Quasi-linear. So we're talking about UTX equals, now I can't remember for sure what the initial condition, what it does, but it has to be kind of non-degenerate. And then you're going to add your Laplacian. And then you're going to add a nonlinear drift. And then the last thing you add is an additive noise. And of course, I wrote it in the same sort of notations as I used over there, but in their paper, they're able to use something which is not a function in space. They can use a distribution up to a certain level. In fact, I think it even works for space-time white noise. And so what they prove is, and so I forgot to say that here x is in 0, 1. So they have some Dirichlet or Neumann boundary conditions. And yes, this is space-time white noise. So maybe we put a dot on top of it. Space-time white noise. This means it's the derivative of a Brownian motion in space, and it's the derivative of a Brownian motion in time. So it's the cross. It's what's it called? The mixed derivative, the mixed second derivative of a Brownian sheet in dimension 2. So d equals 1. And then what they notice is that for fixed t and x, d of the solution solves a linear ordinary differential equation with some randomness in it. Well, I'll write it down so you can see what it is. So maybe you'll be able to see the bottom of the board here. It's not clear, but here's the differential equation. For fixed t and x, you have drz, and I'll explain what the z is in a second here, equals the green function. So you have Green's function here for the original problem without any noise and without any b. And then multiply that by b times u sy. Multiply that by the Malliavin derivative of u sy. Integrate with respect to y and with respect to time.
Okay, very good.
Testing. So you can see that if you assume, which you do, you may assume that you know the solution because the solution is a solution, and then you see that the Malliavin derivative solves an ordinary differential equation. You know, there is this part here which is random, but you're going to make assumptions on B which don't make the problem completely trivial. In fact, it's still quite difficult, but they're such that there's enough non-degeneracy in the problem that you can solve the equation, get a handle on your D, show something of this form. It's actually much, much harder in that example than in the one I just presented here, but it's still feasible. Let me try to write down the assumption on B. I think that B prime has to be Holder continuous. Is that right?
Bounded.
No, bounded. B prime is bounded. So you assume B is in C1. It's a function with a bounded derivative.
Excuse me, Frederi, you forgot some integral in the last equation.
There's no integral. So there's a double integral. Of course, otherwise it's not even a differential equation. And there's also a term which I forgot.
Yeah.
And there's an extra term, which is G. So this should be an S. Well, that's what happens when you present somebody else's work that you admire, but you know. And so I just need to explain one thing, which is that up to now, I've only talked about taking derivatives with respect to in the Malliavin sense where you have only one time parameter, which is in this sort of space. But I kind of cheated a little bit because as soon as you start talking about this example, because your Brownian motion here is a Brownian motion which is in some sense infinite dimensional, you're going to need two, if you want, time parameters. Your little r and then some other parameter. You can call it Fourier if you want. And then here it's the same thing. So here they call it z. And that's not the same z as the z's that we've been talking about before. It's just an extra parameter that you need to make sense of your infinite dimensional Brownian motion. But conceptually, everything that I've said at the beginning in parts 1 and 2, where I introduced these tools, it makes no difference conceptually whether you have a Brownian motion on 0, 1, or whether it's an infinite dimensional Brownian motion. So, so that's what that little z is doing. And so you can see that this solution to this equation is maybe not so nasty since it's simply an ordinary differential equation with a random coefficient right here. And then what they notice so here I'm erasing the Mailer formula. The thing that I'm just erasing here is one of the tools that you need to make the evaluations of gx. It's one of the tools that you need both in this example and in this example. And using that Mailer formula, that consequence of Mailer's formula, they do prove that with x equals utx minus its expectation, we get that in one dimension there exist two constants, C1 and C2, such that the following thing holds. And so what you do is you simply apply this consequence of the density formula, where C is equal to C1 square root of t over there, C prime is equal to C2 square root of t over there, and you're done. You get the following bounds on the density of the solution. So you get that the solution has a density, and you get the following bounds. So you end up with, so they prove the following, and as a consequence, they get expectation of x over C2 square root of t. There's maybe a factor 2 right here, multiplied by e to the negative z minus expectation of x. This is expectation of x minus its absolute value, minus its expectation.
Effective value of x is 0. I believe.
Pardon me?
Expect.
It's, I used the wrong letter. I shouldn't have called it x. Yeah. 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 So you get these bounds, which of course you expected as soon as you saw this statement. There's a square here. There may not be a 2 here. I think it's, I'm not sure. Well, it doesn't matter much because the C's are not well defined. So in other words, you do get your Gaussian bounds. And this is a new result. I mean, people work hard enough just to prove tail estimates for solutions of SPDEs. And so here we have Gaussian bounds. So don't have much time. Maybe don't want to take the entire hour. So I might just finish by saying a few things about what else Newellart and Kerr did in this paper. The constants here, C1 and C2, only depend on the value of x that you're using when you fix your value x. They don't depend on t, of course, and they depend on capital T. You have to give yourself a finite horizon, and they depend on the infinity norm of b prime, and that's pretty much all that you can expect them to depend on in the best of cases. What they also do is they look at the case where d is greater than or equal to 1. Instead of working on compact interval, they work on RD. And here they can't use space-time white noise. They have to use a functional, no, that's not true. They can't use space-time white noise. It turns out, if you consider W, if you put a little dot here instead of an X to signify that your noise is maybe distribution valued, I can tell you that the assumption that they are making in the case where D is larger than 1, for RD, this assumption is that, morally speaking, the antiderivative in space of W is going to be better than, I think it's better than 1/4 Holder continuous. I think that's it. So there's a little bit of regularity that is involved. They work with the spectral representation of the noise W, and they end up with the same formula, the same estimates as we have here, with one exception, which is that it's not sharp in T, because instead of having a T here, they have T to they have here T to a slightly larger power, which is a bigger upper bound, and here they have T to a lower power. I think the powers are here. The power. Anyway, it's a little less sharp. My notes aren't accurate enough for me to make a precise statement. They also treat the case of the wave equation. So here, this is a heat equation, but it's a much more general method that can be applied to any equation in which you can handle the random variable capital G sub x. And it works in the case of the wave equation for small t, but they still get good bounds for small t and dimension less than or equal to 3. And then I was just made aware of a preprint this morning in which in the case of both the heat and the wave equation for small t in any dimension in continuous space, they end up with sharp bounds kind of this sort, except they identify the proper power here, depending on the operator that you're looking at, which is the Laplacian, and depending on the dimension. I believe that's it. So these results were proved using a lot of fairly intense calculations, but when you look at the proof, what you can see is that there's nothing that's really that seems unsurmountable. And the only thing was that, so the whole point of the proof is establishing this sort of inequality, and you have to use tools which I think most stochastic analysts would be relatively comfortable with. So I'm happy to see that this sort of assumption can be verified in a fairly complex problem. And I thank you very much for your attention.
Other questions or remarks? your method seems to be basically one-dimensional.
Yes.
Is there some hope to go to multi-dimensional random variables?
I don't know if there's hope, but there's at least a strategy, which is the paper that I mentioned with Malliavin and Hélène Hérault actually goes back to Hérault's original work and Malliavin's original work, in which we see a formula which is which is not explicit like this, but you end up with a partial differential equation for the density. And this partial differential equation, its coefficients are a matrix of G's. So if you have a multidimensional vector X, then you're going to have a matrix for G because there's an inner product in the definition of G. So it's kind of like a Malliavin matrix. And so you get a matrix for little g, and you use that in your PDE. It's a standard PDE for the density. And so if you have some, but I tried to look at consequences of that PDE under assumptions of this sort, which can be translated in assumptions on little g. And I wasn't strong enough to figure it out. But I don't know if there's hope, but there's a strategy. Yeah.
Just kind of following up on that question, in Rn, it's used for Stein's operator, you use the generator of the Ornstein-Uhlenbeck semigroup, right?
Okay.
So instead of just the single integration by parts formula.
Yeah.
I mean, and so there's a Laplacian there. I mean, is there some way that is what you were just talking about somehow a Laplacian, a Laplacian on, is the SPDE a Laplacian somehow on the Cameron-Martin space, or on
The ordinary PDE, is it a Laplacian?
Yeah, I mean, is that what you're getting somehow? Because I mean, you know what
So-
I'm talking about. If you do the Gaussian
Yeah.
stuff, like the standard stuff of, all the people who do Stein's method, right?
Yeah, which, as I said, I'm kind of a novice at. But yes, I see what you mean. And you would have to have some sort of assumption on G. So I'm certain that, yes, that's a good strategy. Now, whether the assumption that you're going to make on G in order to get something out of that idea is something that's relevant to any problem, I wouldn't be able to tell you.
It's not a question but a comment, but I think that maybe may help to understand better what you have done. So in the general setting of the classical setting of Malliavin calculus, you have an integration by parts formula, and this integration by parts formula gives expression for the density. So this is what Watanabe has done. So it's a complicated formula, but well, the general, if you wish, statement is that when you have an integration by parts formula, you have a formula for the density. So you can also use this formula for the density to analyze the possibility of having upper and lower bounds for the densities of very general functionals. So what you have done here is you have considered another integration by parts formula, because integration by parts formula are not unique. And then using another strategy, you got another formula for the density, which is suitable to analyze, for example, this case. So just to complete what...
That's exactly right. Bang on, as they say.
Well, if there are no more questions, let's have the speaker again.